Welcome back, everyone. In the previous set of lectures, we really discussed setting up our data for sequence forecasting and sequence prediction, which essentially consisted of setting up our training set and then our final test set. Then, from our training set, setting up our batches of data, where we had some sequence of training points along with a corresponding label one time step into the future. Now let's go ahead and focus on building out our actual LSTM model. Recall that in theory our model is taking a long-term memory and a short-term memory, essentially its own internal state, and then also with that it's taking input at time t. What we're going to do is we're going to separate this out into basically two components, the long-term memory and short-term memory, and then the incoming input at time t. Similarly, we'll separate out the output at time t along with the new long-term memory and new short-term memory. So what does this actually look like with PyTorch? Here we can see what the actual LSTM cell unit will look like inside of PyTorch. And the main things to notice here is that this long short-term memory cell, it's doing internally all the computations that we previously discussed. Now the parameters that it's going to provide for us are the input size, which is the number of expected features in the input x. Currently, we've only seen just single time series, that it's essentially one data point per timestamp, which means we have one feature per timestamp. So all our input sizes will be 1. But you can easily expand this if you had 2 input points per timestamp. Then you would have an input size of 2. But if you're just dealing with a single time series, essentially one column of information, then your input size is 1. The hidden size states the number of features in the hidden state h. And then the bias, if it's false, then the layer won't use the bias weights of b of I of h and b of h of h. By default, though, it's going to be true, and we have no reason to set it to false. Now, when we actually create the LSTM cell, it's going to accept inputs and outputs. The input, notice here, it's a tuple, so it's essentially separating out those two components that we just saw on the diagram earlier. The input here is going to be the shape, it's that tensor containing those input features. Then we have inside of a tuple our hidden state and our cell state. Similarly, we have the output. So again, we have a tuple here where we have the first item being the output and the second item being another tuple with the current hidden state and then the current cell state. So hopefully you can see how the input method here and the output method here directly reflect what we have going on with this LSTM cell, where we have essentially a tuple of h0 and c0 along with the input, and then we're outputting a tuple here with output at time t along with h, the new long-term memory, or excuse me, c, the new long-term memory, that's cell state, and then h, that new short-term memory, which is the hidden state. Okay, don't get too confused here as far as using the term hidden, because we're dealing with hidden layers, and then technically there's also a hidden state within the LSTM. So that word hidden gets used a lot of times for different things. So try not to focus too much on that. Instead, just focus on the general idea here that we're essentially inputting 3 items and outputting 3 items. But the way we're going to organize it within Python is essentially a tuple where one of the items in the tuple is itself another tuple with the long-term memory and short-term memory. And then similarly, we'll do the same for the output. Okay, let's head over to the notebook and see how this all plays out. All right, so here we are where we left off last time. What we're going to do is say class LSTM and then inherit from module. And then we're going to instantiate by saying def init pass in self. And then our input size, we essentially just have one y value per timestamp, so our input size is just 1. And then our hidden size, you can kind of relate this to how many neurons you actually want inside the LSTM layer. We'll go ahead and say 50. And then the output size, remember we're just producing one prediction output, so the output size here is just 1. So it's essentially how many different cases of y values do you have? We just have one y value here, essentially a sequence of a single column of time series. So our input size is 1. Then our hidden state is 50, so how many neurons do you want in this? This is something you can play around with. And then our output size, that needs to match how far out you're actually predicting. In this case, we're just predicting one part out. So we'll go ahead and call super and instantiate, whoops, double underscores, init. We'll instantiate that class we inherited from, and then we'll set self hidden size is equal to the provided hidden size from the user. And then the next step here, what we're going to do is we'll set up our LSTM layer. We'll say self.lstm in lowercase and set that equal to nn.lstm, and that accepts an input size and the hidden size as we just saw earlier. And then we'll go ahead and right now we have that layer with 50 LSTM neurons. What we need to do is essentially condense that back down to one single output. So what we need to do is say self.linear is equal to nn.linear, and that takes in the hidden size. Essentially, we have our input, one sequence of values, gets expanded to the hidden size, so essentially 50 neurons inside this LSTM layer, and then from those 50 outputs, we'll go back to a fully connected layer from the hidden size down to the output size, which in our case is just one because we're predicting only one out into the future. Okay, next what we have to do is, because during training we're essentially actually passing 3 tensors to the LSTM layer, we're passing in the sequence along with that tuple of the hidden state and the cell state, that H value and that C value. So what I'm going to do is say self.hidden and set that equal to a tuple. This is where we're initializing our hidden state and cell state that go inside these LSTM neurons. And so we'll say torch.0, or actually torch.zeros, and then we'll say 1 by 1 along with the hidden size, because we initially need this for each of those neurons. And this is going to be a tuple, so we essentially repeat this. Torch.zeros, 1, 1, hidden size. And essentially, this basically sets up what are the initial hidden states and cell states inside of all these LSTMs. And eventually we start updating those as well. So finally, we have our forward method. So what's our forward method going to do? Well, it takes in the sequence along with self, since this is inside of a class. And then we're going to have our first call to this LSTM layer. So what does this LSTM layer actually output? Recall that we can actually do Shift Tab here, scroll down, and remember that the outputs is going to be the actual output along with this hidden state and this cell state. So what I'm going to do is say, here's my LSTM out, comma, and then I'll update self.hidden. So essentially, self.hidden here contains both this hidden state and this cell state. So then we'll say self.hidden is equal to self.lstm, and then we're going to pass in that sequence. So what is LSTM expecting? If we take a look at it, remember, if we expand on this, LSTM, come back down here, it's expecting the input and then the current hidden state and the current cell state. So we'll go ahead and for the input, that's our actual sequence. So we need to view the sequence correctly. So we need to say, take that sequence and view it by the length of the sequence, comma, 1, comma, -1. This is basically so the dimensions line up correctly for the sequence going into the LSTM. And recall, again, the input also needed H0 and C0, that hidden state and that cell state, which we know are already contained within self.hidden. So again, self.hidden, what this is essentially that H and that C, that hidden state and that cell state. And if you wanted to, you could kind of split this up. You could say self.hidden is equal to this, and then say something like self.cell state is equal to that, and not have it be combined as a tuple. But putting them together in a tuple and just calling it hidden, that makes it a little cleaner. So that we can just have it here as self.hidden instead of having 3 things down here and then 2 more things here. Okay, so that's what self.lstm outputs. It outputs our LSTM out, and then that hidden state and cell state, which we've combined into self.hidden. And next, we actually want our prediction. So what is our prediction? Well, our prediction comes out of that linear layer. So we say self.linear, and we take LSTM out. So essentially passing in what was gotten from LSTM out, and then we're going to make sure to view it correctly so the dimensions line up. So say view length by sequence by -1, just in case we end up playing around with that batch size. And then finally, what do we actually care about predicting? Recall that technically what we're going to be outputting is if our sequence was something like 1, 2, 3, and we predicted a 4, what I actually want the LSTM to output isn't something like this, 1, 2, 3, 4. Really what I care about is I just want that 4 value. So what I'm going to do is this prediction is actually going to kind of output everything, but I only want the last prediction. So what I'll do here is I'll say return my prediction, but go ahead and just grab that last value because I'm only concerned about the true forecast. Okay, so we'll go ahead and run that, and there's our LSTM class. Now let's go ahead and instantiate the model, define loss and optimization functions, and the next lecture will actually show you how to train and predict future values. So let's set this up. I'm going to set up a seed, that way you make sure you get the same stuff I do. So we'll set up a torch.manual seed of 42, create an instance of this model. For our criterion, we'll go ahead and because this is a continuous value, we can choose mean squared error loss. Optionally, you could also set this up to be root mean squared error. And then our optimizer, for recurrent neural networks, we have found that SGD actually converges faster for this particular application than the atom optimizer. So we'll go ahead and use an SGD. So we'll say torch.optim.sgd. So SGD, you can check out its signature here by just doing Shift-Tab once you've already imported, but it's a stochastic gradient descent. Okay, so kind of back to basics here. And then we'll pass in the model parameters. And I'm going to set up a learning rate. This is actually not that complex of a problem, so 0.01 should do just fine. Go ahead and run that. Call your model, and it should look something like this. And it's actually quite simple. It's just taking in that input. We have that LSTM layer with 50 LSTM neurons in there. And then what we have here are the in features coming into the linear layer. That's gotten from this 50 here. And the output features is 1. So something you can play around with technically is the hidden size here, since that basically leads from here to here. But 50 for this particular problem, it is kind of just a simple sine wave, so it shouldn't be that complicated to figure out the pattern. So go ahead and keep it at that. As far as how many parameters we have here, we can always say for p in model.parameters, go ahead and print out p.number of elements, run that, and if you were to add these all up, this is 10,651 elements. So it's actually quite small, so we should actually expect this to run pretty quickly. Okay, coming up next, we'll show you how to predict future values. I'll see you there.